Hi, and welcome to part 4 of our Operational Amplifiers series. In this particular episode, we'll take a look at an experiment from Malvino, Electronic Fundamentals. And in that experiment, we'll be looking at the differential amplifier again in the operational amplifier, but this time we'll be measuring with the DMM the input offset currents and the input offset voltage. We'll be measuring the maximum output current available from the operational amplifier, and we'll take a good examination of what happens to the output voltage, which should be sitting around 0 volts. What happens to that if we have a tiny little bit of input offset current / voltage happening at the front of the op-amp? So let's get on with the lab.
This is lab number 42, the operational amplifier. In this lab, I've got two 220 k ohm resistors between the positive and negative inputs going to ground. The first thing you can see me doing here is checking the rail voltages on pin 7 and pin 4 to see that I've got positive 15 and negative 15 volts respectively. Then, while I'm in the mood to do that, I went across to pin 6 and measured minus 12.75. That's not good. I would really expect an op-amp with the same resistances to ground to have the 0 output. And looking at that, I've got 12 millivolts on each of those inputs, but we'll go down to the 300 millivolt range on the DMM and we'll have a closer look, because you know, the high gain of this op-amp, 12.4 to 12.5, I've got on pin 2. 12.5 to 12.6, I've got on pin 3. So it seems that there's around about maybe 100 microvolts. There it is there. Around about 100 microvolts of difference between those two terminals. And 100 microvolts of difference across there with an open loop gain, which is this current configuration, is going to give me around about 20 volts of output. But with 15 volt rail, it can't get that high. Here we go again. We'll have another look at the output. Minus 12.75. It's an inverting amplifier, and it appears that the output has gone negative. So I must have a gross positive input to have that sort of an inversion. So I'm going to change the operational amplifier, and the lab does call for 3 different op-amps to be used. I only have 2 on the day, so I'll get the other op-amp and we'll put it in and we'll run the same tests again and see what sort of figures we get. Okay, the other operational amplifier is now in place. I do note that they're both Philips. They're both probably out of the same batch. They were bought at exactly the same time in a bulk buy. Checking again that I've still got my positive 15 and negative 15 volts. And I do indeed. And like I did before, straight across to pin 6, minus 12.75. Looking at the inputs again, I've got 11 to 12 millivolts. And I've got 12 millivolts, so it certainly would appear there might be more of a difference here. 12.1 millivolts to be more exact on pin 2 and 12.4 millivolts on pin 3. That's a difference voltage there of 300 microvolts or 0.3 of a millivolt. That's a big difference to have at the front of this amplifier when I've got exactly the same resistors going to ground. I really wouldn't have expected to find so much variation within 2 identical op-amps out of the same batch, same part number, same everything. When we set up the second circuit and we calculated that gain of 1000, I just thought I'd explore that a little bit more. We had 100k of feedback resistance. We had 100, well, actually we had 120 ohms because I couldn't find the 100 ohm resistor. So that's 100,000 divided by 120, but we'll do the maths on it based on 100 to show that you've got a feedback of around about 1,000. So look, I'll just bring a calculator in there, and it's going to be 100k, so 100 engineering 3, and then divided by 100, and of course there's our 1,000 times gain. So whatever the output voltage is, if we divide that by 1,000, that'll give us the input voltage, and vice versa. This is an inverting amplifier configuration, of course, so a positive going voltage in gives a negative voltage out, and a negative going voltage in gives a positive voltage out. Now, to the other mathematics that we have in this video segment, 3 things that we have to understand: that we've got input bias going to or coming from each base, depending whether you're talking in conventional current flow or electron current flow. Doesn't really matter, it works both ways. And then input offset current, and then input bias current. Now, input offset current is going to be the base current in the first base minus the base current in the second base. And that gives you a nice difference between the two base currents called the input offset current, which equates to an input offset voltage perfectly. The input bias current is simply the average of the two base currents. And, you know, when you look at the data sheet, you don't actually see what the typical base current is. You've got to do a little bit of messing around to find the base current, and even then it's just going to give a range of values. Yes, so the range of values that we get is simply 90 nanoamps down to 70 nanoamps, and to get base voltages developed across the base resistances, you just have to multiply those out, simple Ohm's law. It really does come down to how big the input resistance is as to how much impact it has on the circuit. Low value input resistances, of course, when you cross multiply this, you're not going to get very big differences in the output compared to if you have bigger values of resistors. Here's the spec sheet, like I said, from the LM747, and it shows the IN bias, which is like an average bias at 80 nanoamps. And by the time we use that 80 nanoamps, going back down through the base resistors, we're going to come up with values very much in the order of this 12 millivolts, 12.5 millivolts, something like that. And they were, in fact, measured values compared to the calculated values over here, which are a little bit higher. In the lab that we actually used, table 42.2 called for us to work out the input offset and bias currents. I've gone ahead and I've done that here. I've calculated IB1 and IB2 and from our measured voltages, and we knew that we had 220,000 ohms of resistance. Minusing one from the other gives me 1.4 nanoamps for IN off. IN bias is the average of the two. OpAmp number 1, OpAmp number 2. OpAmp number 2, this one had a remarkably good IN off. It was only 0.3 of a nanoamp. That's extremely good, because if we look at IN off, typical value is about 20 nanoamps. So at 0.3 of a nanoamp, that's remarkably good. Output offset voltage was where I measured the voltage at pin 6, and in one case I measured 980 millivolts. In case 2 with the other IC, I measured 20 millivolts. And of course, this one was the chip that gave me the lowest V-out offset. It was very, very good. Doing the maths on these didn't quite work out to what I expected. VN off, because we've got a gain in this amplifier of 1,000 times, it should have been V out off, which is 980 millivolts divided by 1,000. That gives me 980 microvolts. But if we go back up to our original values, we had about 300 microvolts between these two, not 980 microvolts. And in the second case, There's about 100 microvolts between the two, yet the maths here says about 20 microvolts, so I'd have to explore that a bit further to be able to explain that. Output current, we measured 32 milliamps on the day. That's pretty good. The manufacturer says 25 milliamps. I saw it drop pretty quickly from 35 milliamps down to 32. It did stabilise at 32. I don't think that there was much room for it to fall much further, but time would have told. All right, let's go on and have a look at the second part of the video lab. I've rewired the circuit for this second segment. In this second segment, I've got two 120 ohm resistors going to ground, and I've got a feedback resistor of 100 k ohms going between pin number 2 and pin number 6, making this a closed loop inverting amplifier. Just checking the circuitry there on the board. There's my feedback resistor going across to pin 6. Also from pin 6, I have a 10k resistor going to ground. You can see that on the top right hand part of the configuration. There it is there, 10k. I also have to use two capacitors in this lab for stability in the circuit, so between positive and negative 15 volts, as close as practicable next to the OpAmp. I've put these 0.030 I put these 0.39 microfarad capacitors down to ground. There's my negative 15 volts, and here's my positive 15 volts. That's always what I would check first when I'm working with an OpAmp. Pin number 2 on the OpAmp. Pin number 2 on the OpAmp, we didn't read anything on the main voltage scale, so we'll go down to 300 millivolt range, and I'm only measuring about 0.1 of a millivolt, not very much at all. It's probably what I'd expect to be measuring there. And pin 2, measuring pretty much the same. So across those two inputs with this IC, they're measuring pretty well both the same, maybe a fraction of a millivolt between the two. At the output, I've got minus 19.7 millivolts. Note I still am on the 300 millivolt range on the meter. So that's telling me with this particular OpAmp in this configuration, the input bias currents, any mismatch there is not enough to give me an offset voltage more than 20 millivolts, which is really good to see. Now, we've got to go on with this lab and check the maximum output current. So what I'll do, I'm going to move across the feedback resistor to the positive rail. You can see me doing it there now. And I'm going to disconnect the 10k ohm resistor off the output. By moving that feedback resistor across to the positive rail, it's 100k ohms and it's going back to a 120 ohm input resistance. That'll give me about 15 millivolts at pin 2. And that's more than enough to saturate the front end of this differential amplifier and drive the OpAmp to one rail or the other. You can see there it is, about 17.5 millivolts. That's great. Just what I expect to get. Okay. All right, setting up a current meter now. Because the current meter has extremely low resistance in the current range and the output of the OpAmp has a very, very low resistance, this allows me to use the current meter between ground and pin 6 to measure the maximum available current from the OpAmp while it's in saturated mode. We're over range on the 20 milliamp range, so we'll quickly go across and change it to the 200 milliamp range and measure it again. Whoa, 34 milliamps, and quickly dropping back as the OpAmp internal circuitry heats up a little bit. So it's probably going to come down and stop at around 32 or 31 milliamps. The manufacturer's specifications do say about 25 milliamps. If we're getting more than 31 or 32 milliamps, we've done really well out of that particular OpAmp. So now we can change the op amps because we are checking these parameters for the pair of op amps that I do have today. So taking this op amp out of the circuit after turning the power off and replacing it with its partner, and then I'll go straight into checking the output current before we measure the voltages. Okay. Whoa, did you see that? Did you see what I just did? And can you see that? There's nothing on the meter. I've made a fatal mistake. The red probe touched onto the rail, momentarily enough to blow the fuse in the current meter. So that means we've got to strip the current meter down and we've got to replace the fuse. All right, I've done that now. I've replaced the fuse. You can see I'm just explaining there what I've done with the screwdriver, touching onto that because the feedback resistor I do have at the moment onto the positive rail. So that's 15 volts. 15 volts to ground. I blew the fuse straight away, and sadly I don't have another fuse, so what I had to do was resort to some aluminium foil. But that was good enough on the day, and that gets us back into action again, ready to take that second reading. All right, so here we are with the improvised repair job, a bit of aluminium foil over the fuse and being very careful not to touch that rail again. Here we are, 34, coming down quickly, 33. It's going to come back maybe a little bit higher than its buddy, 32.5, and it was probably still dropping a little bit further. So both of these op amps out of this batch do seem to have very, very good, strong output current. Not enough to drive a relay, maybe enough to hold a small PCB relay, but not enough for the pull-in current to start the relay into action. All right, now we go back to part one of that lab, and we have to put the feedback circuitry back in to give it a gain of 1000. So putting this feedback resistor back to pin 6, putting the 10K load resistor back to pin 6, and that gives us our 1000 times gain, which is 100 ohms from pin 2 to ground and 100,000 ohms as the feedback resistor. We've powered the circuit back up again, and with the millivoltmeter going between ground and pin 2, we've got 1.1. Ooh, 1.1 millivolts. And into pin 3, 0. Ooh, this is a big difference between the other op amp. Remember, the other op amp had 0 and 0. This one's got 1.1 millivolt of difference between those two input terminals. This is going to be a pretty problematic chip. In the previous example, we only had 20 millivolts of output. Now look, we've got 930 millivolts of output because the input offset voltage is too high, and that's because the bias currents are not equal at the front of this op amp. Remember, the currents flow from the differential bases out from the op amp to ground, and we do have quite a bit of imbalance there. We've got 1 millivolt, which is a very lot of voltage between those two input terminals in this configuration. Problematic op amp that. I wouldn't like to use that in a circuit. It would certainly need to have a voltage offset potentiometer between pins 1 and pin 5 to bring that back to 0.